Hello and welcome. I am Dr. S. Kritika, and in this video we will be covering the topic molecular weight of polymers and explaining the key concepts in a clear and organized way. So in this video we will be discussing about what is molecular weight of polymers and what are the different types of molecular weights and problems based on molecular weight and the important concept of polymer, that is glass transition temperature, melting temperature, and what are the factors affecting glass transition temperature. Polymers are macromolecules composed of repeating structural units called monomers. During the polymerization process, the growth of the chain is random in nature and the product contains a mixture of chain of different length. As in a polymer, there is a spread or distribution of different polymer molecules of different chain length, and hence the molecular weight of the polymer is given as an average molecular weight. The molecular weight of the polymer is expressed in different ways depending on the method of measurement and its application. The three important methods in which it is expressed is the number average molecular weight, weight average molecular weight, and viscosity average molecular weight. Let us discuss about the first one, number average molecular weight. The average molecular weight of the polymer is calculated by dividing the total molecular weight of all the polymer molecules by the total number of molecules in the sample. It is mathematically expressed as summation of NiMi by summation of Ni, where Ni is the number of molecules with a molecular weight Mi. It gives more weight small molecules and it is commonly measured using osmotic pressure or N-group analysis method. The second one is the weight average molecular weight, which is expressed as the summation of NiMi square by summation of NiMi, where Ni is the number of molecules with a molecular weight Mi. So usually MW is typically measured using light scattering or ultracentrifugation and provides insight into the mechanical and rheological properties of the polymer. The third one is the viscosity average molecular weight. The measure of the polymer's molecular weight based on its intrinsic viscosity in solution is determined using Mark-Hornig equation. According to Mark-Hornig equation, neta is equal to Kmv power A, where neta is the intrinsic viscosity and K and A are the empirical constants, where Mv is the molecular weight based upon the viscosity. Usually MV lies between Mn and Mw and it is commonly measured using viscometry. Next one is the polydispersity index. So polymers usually have a distribution of molecular weights, and the polydispersity index is a measure of this distribution, which is defined as the ratio between the weight average molecular weight and the number average molecular weight. When PDI is equal to 1, it is for perfect, then it is perfectly uniform polymers. When PDI is greater than 1, it's for more synthetic polymers, indicating a wide spread in molecular weight. The next is the molecular weight distribution of polymers. So this diagram represents the molecular weight distribution of a polymer, showing the weight fraction of the polymer molecules as a function of the molecular weight. Polymers are composed of macromolecules with varying molecular weights, leading to a distribution rather than a single molecular weight value. So the distribution curve is skewed with a peak at Mn, and Mn is the lowest among the three averages, followed by viscosity average molecular weight and weight average molecular weight. This ordering follows the general trend that number average molecular weight is less than viscosity average molecular weight, which is less than weight average molecular weight. The polydispersity index is given by the ratio between weight average molecular weight and the number average molecular weight, which indicates the breadth of the molecular weight distribution. A higher PDI means a broader distribution. Degree of polymerization represents the average number of monomer units in the polymer chain, and it is an alternate way of expressing the average chain size of the polymer. Both the average dPn and the weight average dPw, degree of polymerization, are defined as the number average degree of polymerization is defined as the number average molecular weight divided by the molecular weight of the repeating units. The weight average degree of polymerization is defined as the weight average molecular weight divided by the number of molecular weight of the repeating unit. Now let us solve some small problems in weight average molecular weight, number average molecular weight, and viscosity average molecular weight. First problem, the statement of the problem is a polymer sample consists of three types of molecules with the following distribution. So this is the distribution they have given, three different molecules with the three different molecular weights, 10,000, 50,000 and 1 lakh, with a number each having the number of molecules of 50, 30 and 20. And they are asking us to calculate the number average molecular weight, weight average molecular weight and polydispersity index using the given data. Next, let us go. Now let us go for the solution for the problem. So in the current problem, the different molecular weights with different molecules are given. First, let us compute the number average molecular weight. Number average molecular weight is summation of Ni by summation of Ni. First, let us compute the numerator and then go for the denominator. So first numerator is NiMi, that is 50 into 10,000 plus 30 into 50,000 plus 20 into 1 lakh, which will give you the 40 lakhs. Then summation of Ni is 20 plus 30 plus 50, which is 100. Then compute Mn, which is 40 lakhs by 100, that is 40,000 gram per gram mole. Next, let us go for the average molecular weight. Average molecular weight is given by summation of NiMi square by summation of NiMi. So first let us go for the numerator, that is sigma summation of NiMi square, that is 50 into 10,000 square plus 30 into 50,000 square plus 20 into 1 lakh square, and then compute the denominator. So denominator is some sigma of summation of NiMi, that is 50 into 10,000 plus 30 into 50,000 plus 20 into 1 lakh, which is 40 lakhs. Then compute molecular average weight average molecular weight by dividing the numerator by denominator. So which will give you 70 lakhs gram per gram mole. After that, calculate polydispersity index, which is the average of weight average molecular weight by number average molecular weight. So the weight average molecular weight is 70,000 divided by number average molecular weight is 40,000. 70,000 by 40,000 is 1.75. The second problem is based on the molecular weight determination using the intrinsic viscosity. The given data in the problem is intrinsic viscosity is 1.2 dl per g and Mark-Hornick parameters are K is 1.5 into 10 raised to the power minus 4 dl per g and A is 0.75. And they are asking us to determine the molecular weight of viscosity average molecular weight MV. And we know the Mark-Hornick equation neta is equal to kmv power a. So substitute all the given data in the problem, that is neta is 1.2 and k value is 1.5 into 10 raised to the power minus 4 and m power 0.75. Rearrange the values, divide the equation and take powers on both sides. We will get the answer as 1,60,000 gram per gram mole. The third problem is based upon the determination of intrinsic viscosity using the given data. The given data is molecular weight, viscosity average molecular weight is given to be 5 into 10 raised to the power 6 gram per mole, and the Hornick parameters are K is 2 into 10 raised to the power minus 3 dl per gram and A is 0.75. So to determine the intrinsic viscosity, we use the Mark-Hornick equation, that is neta is equal to kmv power A. Now substitute all the values given in the problem, that is K is 2 into 10 raised to the power minus 3 and viscosity average molecular weight is 5 into 10 raised to the power 6, the whole raised to the power 0.65. So the viscosity value was found to be 45.22 dl per gram, that is deciliter per gram. The next important concept in the polymer chemistry is the glass transition temperature. When plastic or rubber is cooled up to certain temperature, it becomes so hard and brittle that it breaks into pieces on application of stress. The temperature below which the polymer becomes hard, brittle and glassy and above which it becomes soft and flexible is known as glass transition temperature. So the glass transition temperature is a property of only amorphous portion of a semicrystalline solid. So usually the crystalline portion remains crystalline during the glass transition. The value of Tg depends on the mobility of the polymer chain, and for most synthetic polymers, the range lies between 170 Kelvin to 500 Kelvin. The transition from the glass to rubber-like state is an important feature of polymer behavior, marking a region of dramatic changes in the physical properties such as hardness and elasticity. Next one is the melting temperature. When a polymer is heated beyond the glass transition temperature, it changes from glassy state to rubbery state. Further heating causes melting of the polymer and it starts flowing. The temperature below which the polymer is in rubbery state and above which is it in the liquid state is called as the melting temperature of the polymer, while the temperature at which the polymer starts flowing is known as its flow temperature. Next, let us discuss about the effect of temperature on polymer. The hard and brittle state is the glassy state and soft flexible state is the viscoelastic state. If viscoelastic state of polymer is heated further, the polymer becomes a viscous liquid and it can flow. This state is known as viscofluid state. Below the glass transition temperature, the molecules in the polymer do not move apart and do not have movements within the molecular chains. Therefore, a stress transfer property is lost and the polymer below glass transition temperature is brittle. And above glass transition temperature, the polymers in the viscoelastic state have flexibility or stress transfer properties. Above the melting temperature, the kinetic energy of the polymer molecule is high enough to cause movement with the chain segments as well as to move from one position to another. Therefore, this state has flow character like liquids. Next, let us discuss about the factors affecting the glass transition temperature. The first factor which affects the glass transition temperature is the chain flexibility. Flexibility significantly impacts glass transition temperature. More flexible chain leads to lower glass transition temperature, while stiffer chains results in higher Tg. The second one is the intermolecular interactions. Usually, intermolecular interactions along with factors like chain flexibility and molecular weight significantly influence the glass transition temperature of the polymers. Stronger interactions and increased chain stiffness generally lead to higher Tg values. The third one is the polarity and hydrogen bonding. Polarity and hydrogen bonding significantly influences the glass transition temperature by affecting intermolecular interactions, which in turn restrict chain mobility and increase the temperature required for the transition from a glass to a rubbery state. The fourth one is the presence of bulky pendant groups. Bulky pendant groups generally increase the Tg of a polymer because they hinder chain rotation and flexibility, thus reducing chain mobility, and it requires higher temperatures for the transition to a rubbery state. And the fifth factor is the presence of flexible pendant groups. The presence of flexible pendant groups generally decreases the glass transition temperature of a polymer as these groups increase chain mobility and reduce intermolecular attractions, allowing the polymer to transition to a rubbery state at lower temperatures. The sixth one is the molecular weight. Higher molecular weight polymers generally exhibit higher glass transition temperature due to increased chain entanglements and reduced mobility, while lower molecular weight polymers have lower Tg values due to increased chain mobility. The next one is the copolymerization. In random copolymerization, factors like chain flexibility, intermolecular interactions, and the composition of the copolymer significantly influence the glass transition temperature. The next one is the cross-linking. Cross-linking usually increases the glass transition temperature of polymers by restricting chain mobility and increasing rigidity as the covalent bond between the chains hinder free rotation and segmental motion. The next one is the plasticizer. Plasticizer increase free volume between the polymer chains, allowing them to slide past each other more easily at lower temperatures. The next one is the water or moisture content of the polymer. Water or moisture content in the polymer acts as a plasticizer as it reduces the glass transition temperature by increasing the chain mobility and disrupting interactions between the polymer chains. The next one is the effect of entropy and enthalpy. Glass transition temperature is influenced by entropy, which is the degree of molecular disorder, and enthalpy, which is the intermolecular interactions, where higher enthalpy and lower entropy raise Tg by restricting molecular mobility. The last one is pressure and free volume. Increase in pressure of surrounding leads to decrease in free volume and ultimately high glass transition temperature. The significance of glass transition temperature. So the glass transition temperature is directly proportional to the molecular weight, cross links, intermolecular force and side groups. And the glass transition temperature is inversely proportional to the flexibility and plasticizer. So in this session, we had a detailed discussion about molecular weight of polymers and the three different ways in which molecular weight is expressed and simple problems based on molecular weight and glass transition temperature, melting temperature, and what are the factors affecting glass transition temperature. Thank you.